So let's continue our discussion about the uniform spanning tree. I'm reminding you we have a connected finite graph G. We look at the set of all spanning trees, which are a subset of edges that contain no cycles. They are connected, and every vertex is represented as touched by an edge, right? And we choose one of these at random. And the first thing that I promised you is a theorem due to Kirchhoff, which is, I think, the only thing that I know in English which has two consecutive H's in it, and it's from 1857. So it's a pretty old result that says that the probability that E is in the UST, a particular given edge, right? So I'm not writing all the G is a connected graph, etc. T is or the UST is a randomly chosen uniform spanning tree. E is an edge xy. The graph need not be simple. Okay, so even if there are many edges between the two vertices xy, still the probability, right, is the effective resistance in the graph between x and y. Right? And this is indeed a number less than or equal to 1 because there's an edge between x and y, and it's a resistance, so it's bigger or equal to 0. Let's see the proof of this fact. And this fact is indeed the main reason why this model, we can say a lot of things about it, and why this model is very interesting in all sorts of settings. In the two-dimensional setting, the UST has a lot of contemporary breakthroughs. Its shape is governed by a conformally invariant process, SLE2, and a lot of these facts come from the fact that these quantities, right, resistances, harmonic functions on the plane are conformally invariant. So this is really the starting point of this theory. I'm presenting to you a slightly different proof that I'm afraid to say I don't know who to attribute it to. I stumbled into it, but and that's it. So here's the proof. All right, so I'm going to define a function. I'm going to define an antisymmetric function on the edges of the graph. So define f from the directed edges of the graph to R, and f of an edge E, right, not necessarily the same edge, is going to be the expected net number of crossings of the edge in this direction in the unique path between. Okay, so I need to define. I also need to take two vertices, two arbitrary vertices, A and Z. In A, Z belong to V of G. I take two fixed vertices that later I will choose them to be X and Y. I choose two fixed vertices, and I note that if I draw any spanning tree, it defines a unique path from A to Z. Unique directed path from A to Z, right? Because this is a property of the tree. You cannot have two paths because it will generate a cycle, and you have to have at least one path because this is a connected graph. So f of E is the expected number of net crossings of E in the unique path A to Z in the UST, in a uniformly drawn spanning tree. And what is this net crossing? So this number is +1 if A to Z, right? If the unique path from A to Z crosses E in the right direction. It's -1 if it crosses E in the other direction, right? And it's 0 otherwise. Okay? So really, this is just the probability that the unique path crosses the edge this way minus the probability that it crosses it the other way. Okay, is the definition clear? Right, so all we're using is the fact that there is a unique directed path from A to Z. And let's observe some basic properties of this function. So what I will claim is, so firstly, notice that f is antisymmetric. Right? So, and secondly, f is a unit flow. Right? Because, for each vertex is a unit flow from A to Z. Right? And what is the reason for that? It's a random path from A to Z. It's a random directed simple path, and we proved that any such path is a flow, right? Because for each vertex you have one edge coming in and one edge coming out, or zero edges coming in and out, right? In the unique in each path. And from A, right, you have only one edge coming out, right? So it's a unit current flow. Sorry, it's a unit flow. We haven't shown that it's current. So these are obvious things. But now I claim that in fact this is an electric flow. This path. So this is clear. And now the claim is F satisfies the cycle law. Right? Meaning that if I have any directed cycle in my graph, E1, E2, E3, EM, and these are all directed, right? Then the sum of F of EI in the direction of the path, in the direction of the cycle, I from 1 to M is 0. Okay? So if I know this, from what we proved, a flow satisfying all this is what we call the unit current flow. Right? And what is this? So if we know this claim, assuming the claim, we are done. Why is that? So let us remind ourselves. So let's take now, and the reason is we take A to be X, and and Z to be Y. Right? So we have this XY edge, right? And we have this whole graph here. But this is the source and sink of our unit current flow. And I'm reminding you that any current flow comes from a voltage, right? So that's what we proved, that there is a one-to-one correspondence between these things. So if we have this unit current flow, it comes from a voltage. What are the two values of the voltage? Voltage is determined by its two boundary values. So if the voltage if the voltage corresponding to the unit current flow has 0 at X, what will be the value at Y? Sorry? No. 1 over just the resistance, right? Just the effective resistance. So if we have a voltage that puts 0 in A and the effective resistance at Z, it induces a current flow that has strength 1, right? Do you remember that? I can barely remember that, right? Because if it's 0 and 1, then the strength is 1 over the resistance. So I multiply it all by the resistance, and I get that. The way to remember it is just remembering Ohm's law, right? V equals IR. The voltage difference equals I, the current, times the resistance, right? And the resistance is the effective resistance in the whole thing. I is 1, right? The amount of current. So here we will have the value 0, and here we will have the resistance, right? So what this means is that, right? So now so what this means is that F of the edge E, so F of the edge E, and notice that when I look at so before, assuming the claim, when I look at the value of F when it's this edge, right, and X is A, right, and y is z, f can only receive, right, the value, the path can only go in the positive direction, right? So this means that f of e, when e are the two, when e is the edge that is the source and the sink, one end of it is the source, one of it is the sink, is exactly the probability that that e is in the UST. Okay, f in this direction, from x to y. Right, so we're wondering what is the value that is written on that edge. The value is just the voltage difference on that edge. And so the voltage difference will have to be the effective resistance. Right, so this will be, this is, what goes on that edge, and this is the effective resistance because it is an edge in the graph. Right, and the reason is, the unique path from A to Z cannot go, this cannot go in the other direction. Right, so the -1 in this has probability 0. Right, so it can only be 0, perhaps it goes another way, or it goes, or receives a +1, and this is the probability. Okay, so the only thing, is anyone unhappy? No, sorry. Does anyone not has questions about this argument? Right, so the only thing I need to show you is that f satisfies the cycle law. Right, and there's some combinatorial identity and reason that guarantees this thing. So let's prove the claim. So proof of claim. Right. So this is what we need to prove. We need to prove this thing. Right. The sum of these values over the over a cycle in a tree is 0. Okay, so let's observe. So there's a nice combinatorial trick to this. So we denote the cycle by E1 up to EM, and it has a certain orientation. And let T be a tree, be a spanning tree. That uses the edge EI. Right? So now I'm looking at a particular tree, right, that uses, say, this edge, E2, in this direction. So perhaps it has this edge, perhaps then this edge, and then it continues here to Z, and from here it continues to A. Right? So I'm looking at one particular tree, right, no randomness. And I want to transform it, right? So I will transform it. And I will call this transformation, say, phi, into a tree, into a new tree, T prime, spanning tree, that does not use EI, but uses EJ in the other direction for some j in the j between m and 1. And it will turn out that this transformation is injective. So two different trees will move to two different trees, and that will be important for us. So what is the transformation? So let's draw the tree T. We'll draw it in pink, say. Right, this is A, and this is Z, and perhaps there's stuff here, right? And it uses it uses this edge EI, E1, say, in this direction, and perhaps later it uses E3, right, and so on. And perhaps a part of the cycle is the edges of the cycle need not all of them be in the tree. So what I do is I take the tree drawn here in pink, and I erase the edge E1, right? And now I have two connected components, right? When I erase an edge from a tree, I have two connected components. And I start traversing, right? Let's choose blue. I start traversing the cycle. The cycle is somewhere here, right? The cycle here is in blue, right? And I start from E1, I go to E2, I go to E3, I go to E4 until I visit the first edge. This one is what I will call EJ, the first edge. So here there was going to be an EJ, right? In the direction of the cycle that connects the two connected components. So perhaps it will be something like this. Right? There has to be such an edge, right? Because if I erased E1, right? Eventually, if I complete a full cycle, eventually I will return to E1. And this could, so it's possible that I just return E1, right? It could be that the cycle can even be, just one edge back and forth, E1 in this direction and E1 in that direction. I have no problem with that. So the cycle could contain two edges E1 in both directions, right? But if I go over the entire cycle, at some point I will return to E1. So there must be the first point, either E1, that the edge of the cycle connects the two components. Right? And this is the edge. So now I add, since I erased the edge E1, I add the edge EJ, right? And this gives me the new tree T prime. Okay? And okay, is the transformation clear to everyone? Before we, yes, question?
Is the EJ unique?
EJ is determined, if I know what T is, then EJ is determined uniquely, because I said it is the first time, right? I start from the end point of E1, start going on the cycle until I go on the cycle, right? E1 to EM until the first edge that connects the two pink parts, right? So this is the transformation phi, right? So if I'm telling you what is T and what is EI, right? So I have to tell you not just the tree T, but also what is the edge, right? Then I'm producing uniquely a tree T prime and an edge EJ that I'm using in the other direction, right? And let's notice that this is a reversible thing, right? If I'm giving you T prime and EJ, right, then the tree just looks like that. I can go on the other side of the cycle, right? I can erase EJ, right, and go on to the other side of the cycle until I see the first edge that connects the two pink parts, right? So this is a reversible transformation, right? So if I give you if you give me T and EI, then I can construct T prime and EJ, and the other way around. If you give me T prime and EJ, I can do it the other way around, right? So what this means is that if we let Ti be the set of all trees, spanning trees T, and the number I, such that T uses EI, right? So what we have, so this phi that we defined, right? Phi is a map from Ti, right? To right? It's to the set Tj, or let's call it T prime j, such that T prime uses EJ and in the other direction. It's not onto, right? I didn't claim that it was onto, right? But all I'm claiming is that phi is injective. Okay? Phi is injective, and of course, and that's it. And this is all that I need, because now if I want to prove this, so let's write this term on the left-hand side, and so now I'm writing the term I from 1 to m of f of EI, right? And I'm reminding you, this is something, right, f is the probability that the unique path from A to Z, right, crosses that edge EI in the direction. So this is 1 over the number of spanning trees. Right, this is a probability, right? It doesn't matter. I sum over all the t's, right? And I sum over all the i's, right? And now I want to, right? So here I will write f of TEI, right? One indicator, the indicator 1 if t uses EI in the right direction, and minus 1 if t uses I in the negative direction. Right, so I'm just going to write it in the other way around, right? I'm just going to split this, the plus and the minus, into two separate sums. So this will be the indicator, right? This is not that t uses EI, right? For the unique path from A to Z, and I also need to add the minus, right? So minus 1 over the number of spanning trees, the sum over the trees, sum over I of t, the indicator, t uses EI in the negative direction. Yes?
Sorry, I don't get the definition of TI.
So TI is the big TI or the
big TI. So it's
the big TI. The big TI is a set of pairs, right? It has the pair.
But right now, what the condition doesn't depend on I, right?
It does. It has a set T, and you put the number I as a part of your pair, because if I just put here a spanning tree, it could be. Sorry?
Just read what you wrote.
T uses EJ, it says right now.
Oh, I'm sorry about that. Okay. T uses EI. Thank you.
With the arrow like this.
With the arrow like this, yes. Thank you. And here, TJ, this uses that. Thank you. And thank you for making it short for me. You should be strict with me. Read what you wrote. It'll be shorter. Does that answer your question?
Yes.
All right. So where were we? So we were here, right? So now we notice that's what's written here, and I want to show that this is 0. So let's just ignore the normalizations, right? I'm dividing by the same constant, so let's ignore it. So the first term, right? This term, the first term is exactly the sum over I, right? And the cardinality of the set T, big TI. Right? And what's written here, I'll first change the notation to make it, instead of calling this I will call it J. Surely you will agree that there's nothing going on here. And what's written here, and I have here a minus sign. What's written here is the cardinality of the disjoint union of the image of the image under phi of Ti. Right, and I from 1 to m. Right, what's written here is all. What's written here is all the trees, all the pairs Tj, such that T uses J in the other direction. Right, and what we proved is that these two sets. Right? This is also a disjoint union of sets. These two sets have the same cardinality. Okay, and hence this is 0. Right? Because phi is a bijection onto its image. Right? So it's unclear for each Ti. It's unclear what is the image of phi. Right? It could be for each little t in I, it could give you a different j in which it returns to you. But we do understand that if you take the union of all ti, the disjoint union, it is a bijection exactly on this set, on the set of all trees that use some j in the other direction. Right? And these have the same cardinality, so you get 0. And the proof is concluded. Yes?
So you claim that the union is disjoint, or you?
The union is disjoint, right? Because The first union, this,
Yeah.
right? Because I have here an I, right? That's why I took the pairs, right? So for each Ti and Tj have to be disjoint if I is different than j. This is not the big Ti is a set of pairs.
On the picture, like E1 and E3, they lead to the same AJ, right? No?
Sorry? Yes, if I have yes, you're right. If I have, right, it sends you the same edge, but it gives you a different tree in the image, right? So here I will have this tree, right? But here I will have this tree.
I understand.
Okay?
Thank you.
You're welcome. Okay, great. So now, so this is the basic thing that we know that gives us a wide control over the distribution of a uniform spanning tree. And before we continue to taking limits of these on infinite graphs, as I promised, I want to discuss one more very important feature of the uniform spanning tree, which is nice to understand. And this is what's known as the Markov property of the uniform spanning tree. So this is, again, very important. It's a very basic, you can call it spatial property of the tree that is inherited, and it exists both in the infinite models or in scaling limits of these things. And this tells you, how do I sample a uniform spanning tree conditioned on an edge not being in the UST? Right? Now we know the probability of this event. I want to condition on this event. I have a general graph. I remove, I have I have an edge, and I want to sample from the conditional probability space the uniform spanning tree condition not to have this edge. What do I do? Sorry? I remove the edge and sample a UST from the remaining graph, right? It is obvious because it's just the same number of trees. And this is what, another big name for the Markov property, right? Markov property of UST. And it's, even though it's completely trivial, it is very useful to define limits and to study this. So if we want to, if we look at the UST, I'll write it slightly informally, but it should be clear. The UST conditioned. So again, we have a finite connected graph. The UST conditioned on the event E does not belong to UST. Right, that the edge does not belong to the tree that you've drawn. This has the same distribution as UST on G when I erase the set E. Okay? So now if I have an edge E and I want to condition on the UST, condition on the edge that is in the uniform spanning tree, what do I do now? Yes, this is the correct thing. I contract this edge, right? UST, right? And this is just an observation, right? So this means that if I want to draw, a UST condition on this edge being here, then I look at the graph where I glue the two vertices, draw a UST on that, and then simply unglue the vertices and return the edges, and return that edge that is there, and what I get is sampled exactly like the UST. And the reason is completely trivial. The number of spanning trees in the graph in which this edge has to exist, and the graph in which you contract this edge, is just the same number of trees, right? It's a completely obvious thing. Okay, so that's why everything works. Okay, so the UST conditioned on the event that edge is in the UST, right, has the same distribution as UST on G with E glued. Right? By glued, I mean I'm gluing the two endpoints, right? Just like the food that we're eating here. Okay, right, and this of course works for if I'm conditioning not just on one particular edge, but on several edges, right? If I want to condition on these edges are closed, and these edges and some other disjoint set of edges are open, then I erase the edges that I conditioned to be closed, I contract all the edges that I conditioned to be opened, I get a new graph, I draw a UST on it, and then I unfold it back to what it was, and what I get in distribution is the UST conditioned on this complicated event. Okay, so this is a good thing. All right, so now we are ready to define the limits of UST on an infinite graph, and lucky for us, we did all the hard work in the last few weeks. So this is not so hard to define, right? And it just follows from the existence follows from abstract nonsense, right? So the infinite limits of USTs, and as I've said, these limits are going to be measures on infinite subsets of your infinite graph. They're going to come from uniform spanning trees. And it's easy to see, as we said, that they have to be spanning and what else? Spanning and have no cycles, but it's not clear that they are connected, right? So this is going to be the basic question. So let's just say G is an infinite connected graph. As usual, locally finite, right? We're not dealing with anything else. And Gn is an exhaustion, right? Gn is an exhaustion. Right, then, so it's a theorem, but we already know the proof of it due to Robin Pimentel, right? That the limit of the UST on Gn exists. Right. So what does this mean? Each of these objects here, UST subscript Gn, is a measure, right? Is a measure on a subset of the infinite graph, right? On subset of edges, right? It tells you, okay, these edges are here, these edges are not, with some probability. And when we take a limit, that means that the probability of any finite, so if I look at the probability that this edge is here, this edge is here, this edge is not here, then these probabilities converge. Right? And if we know that there is such a convergence, we apply what's called Kolmogorov's consistency theorem. Right? If you know that any finite dimensional marginal of your measure exists, then it follows that the infinite thing exists, right? And that means that you can draw just the infinite set of edges, right? Some of them are open, some of them are closed, right? And this is what it means. So all we have to show to prove is we just need to show that the status of any finite fixed set of edges in your graph G, the probability on them converges. So we just need to show, for instance, for one edge, that the probability that a particular edge is in the UST of Gn converges. Right? And why is that true? We already said that yesterday. An exhaustion is a growing sequence of graph, right? And the probability that an edge is in this, the UST is just the resistance between x and y in Gn. But since Gn is growing, the resistance between x and y is decreasing, right? So this is a bounded, so the probability that one edge is there is a bounded decreasing sequence, hence it must converge, right? Secondly, how do we check? Now, okay, this was just the finite dimensional distribution. Now I want to take two edges in my graph and check that the probability that both of them are open, or perhaps this is open and this is closed, let's just say both of them are open, that this also converges, right? The intersection of two of these events. So why does that follow? Yes, right. So these are two fixed edges, right? So after a certain n, Gn contains these two edges. What is the probability that the first edge is open? Right? It's just its resistance. Then I shrink that edge and condition on this event. What is the probability that this edge is open? Right? It's just the effective resistance in the graph that I shrunk. Right? And now I take a limit as Gn goes to infinity and discover that these are also decreasing events. Right? And so if I proved it for 1 and 2 edges, obviously the same idea works for any number of edges, and we get that the limit always exists. Right? So this limit exists. Right? This argument that I told you without writing anything, it just follows from the monotonicity of of the effective resistance follows from what we called Riley's monotonicity. Monotonicity. Okay, that's a too long word for me, so I won't write it again. So this limit, we got immediately this limit exists, and let's, as we said before, let's write its properties. Okay, so let's give this limit a name first. Okay, so properties of this limit, as we said, properties. So one, almost surely, it is it is spanning. So we're drawing a random set of the edges of G, right, such that every vertex is touched by some. Every vertex will have, with probability 1, every vertex will have some edge touching it, right? Just because this is something local, we could check, and right, as we take Gn to infinity, this holds with probability 1 once n is large enough, right? So it goes through the limit. Second thing is that almost surely, so this is a random, right? A random set right? It's a random set in 2 to the. So it's a random set of E of G, of the infinite graph, right? It's a countable set. So it's almost surely spanning, and it is almost surely has no cycles. Right? So this random set will not contain a cycle because the number of cycles is countable, and each cycle from a certain n that contains this, right, has probability 0 of being in the UST of Gn. So the probability that this cycle is in the limit is going to be 0 as well. But we cannot say anything about the connectivity of this object, and indeed, the connectivity finding criteria. This is the number one question in this area for this object, right? And if I give you a graph G, can you tell me a simple way of looking at the graph and telling me, is this object connected or not? So right, and it's obviously the number one question because this is the first thing that you ask yourself when this limit occurs, when you construct this limit, and this is open. There's no known criteria, that I can check. So number one question. Okay, so but you can tell me, you can be smart and tell me, okay, the criteria is clear. If you perform this limit and you get that it's connected, then it's connected, and otherwise it's not, right? Okay, so let's ask a better number one question. It is not even known if this is a 0-1 event. Right, what a bummer, right? So if you're giving me a graph, any graph, it is unknown whether the probability that this random subset is connected is a number that is either 0 or 1, right? So number one question is 0-1 law, 0, let's just write it even without the terminology, is the probability that connected, and let's even give this limit a name, okay? So the limit, so I'm not going to call this limit the uniform spanning tree of G because it's not necessarily a tree. It could be a tree that is not connected, which we call a forest, right? So that's why in the title of yesterday I wrote trees/forest, right? We always start with trees, but in the limit we could end up in a forest, and we know, I haven't proved it to you, we know that this could happen, and indeed in Z5 what you get is a forest. So we'll call it the uniform spanning forest. But this particular thing I will call the free uniform spanning forest. Why do I call it free? So the number one question is the free uniform spanning forest connected number in 0 or 1? Sorry? Oh, sorry. Thank you. USF. USF. Right, uniform spanning forest. Okay, so we don't know whether it's connected or not. This is known for any example that you give me. I will probably, after spending enough time, will be able to tell you. I don't know even of an example in which this is of a particular graph which we don't know. But we don't have a proof that works for any graph. So it's known for all Cayley graphs, all transitive graphs, all planar graphs that I will show you the proof for it, or in some sense all planar graphs. And the reason that I'm calling it free, why do I call it free? Yes? Right, because I didn't put any boundary condition. So indeed, there's a different limit that you can take in which you take an exhaustion and wire and add a new vertex on the outside and connect it to all of the boundary. And this is not just for fun we do it. This is actually, in some sense, a much more natural model than this. And in some cases, it allows us to say something about this model, the free uniform spanning forest. So let me say just a few words about this limit. Question?
Maybe a comment, I don't know if it's interesting. In the properties, every tree is infinite also?
Yes, that's also true. And this is so let's add this property here, right? So 3, almost surely any tree of the USF is infinite. Right? So just to make sure that you cannot get a finite tree. Why is that? Right. If I look at the number of finite trees that are subsets of G, this is a countable set. Right? And for each of these fixed tree, there's going to be an n large enough that contains all of it with room to spare. And then with probability 0, you will see a subset of vertices and edges that are disconnected. Right? So so you will not get this tree. From a certain end, the probability will be 0, countably many such events, and you get that this holds. Right? So it's always a collection of infinite trees. Okay. Any other questions about this basic properties of the USF? So let's discuss one more method of taking a limit. And it's, as I said, this is also natural and also...
May I just ask one question? You
Yes.
said that it's known for translation invariant, for what do you call them? Group invariant graphs?
Transitive,
Cayley graphs,
nice graph.
Is it known for unimodular graphs?
It's known for unimodular graphs as well.
There is there one.
Sorry?
There is there one law for it.
There is a 0-1 law for unimodularity, for any, and I said for any example. Oh, so but is there a proof for all Yes. So
For all
yes, for
unimodular
all
graphs.
local.
I'm saying that if G is unimodular,
Yes.
then
Yes.
there is a 0-1 law.
Yes. So it's only unknown in
So
some.
you have to take your graph very, very inhomogeneous, so large. If you want to construct a counter.
So it is. I don't. Of course, I believe this is true, right? Yes, and I don't know anyone who thinks otherwise. So if you construct an example which is not, then many people, including myself, will feel stupid, which is the ultimate goal in mathematics, to make others. All right, so let's discuss the wired uniform spanning forest. Right, so again, G is an infinite graph. Gn is an exhaustion. I call Gn star is going to be a star exhaustion. So this is a definition. I'm just calling it a star exhaustion. It's not exactly an exhaustion of the graph because Gn star is not a subgraph of the infinite graph. It's simply I construct it from Gn by I identify or glue identify G minus Gn. So all the vertices outside of Gn I identify into a single vertex. Identify G minus Gn into a single vertex. right? And leave all the edges, right, that we're going outside, right? So if I have Z2 in the background, right, I imagine that I plotted here a picture of Z2, and this is Gn, right, a 3 by 3 star. This is Gn. I'm adding, everything that was outside, I'm adding it as a new vertex. So let's add it in orange, right, and connecting it to all of the edges that used to be there, right? But because I identified, I'm never erasing an edge. I've just identified everything, right? So all of these edges now go to the one vertex, right? This is G3 star in this particular example. G3 star. So it is not a subgraph of G, right? But we can take, so the theorem of Robin, which we prove in the same way, is that the limit of the UST on Gn star also exists. Why is that true? So it's the same monotonicity, right? There has to be a monotonicity, right? I'm looking at this edge here, let's say, x and y. Let's just prove it for one edge. And I'm looking at the resistance between x and y as I'm growing my graph. Right? And if previously this resistance, the probability, was a decreasing function, now it's going to be an increasing function. And why is that? And the reason is because I could take G4 star, right? So now from G3 star, let's obtain G2 star. And I could just obtain it by gluing vertices, right? I can take all of these, let's say if I want to get this 2 by 2, right? I can glue all of these vertices here, right, to a new, and this vertex here, to a new vertex, and I will get G2 star, right? And when I'm gluing vertices, I only decrease the effective resistance, right, between any two vertices in your graph, right? So I've decreased the resistance, hence the sequence, I decrease the resistance when I'm going from G3 to G2. Hence, the sequence of resistances as n tends to infinity is decreasing. No, it's increasing, right? It goes the other way around. So right, it is if it is decreased when I'm going from G3 to G2, it has increased when I'm going from G2 to G3. Okay, problem solved, right? Okay, so the limit exists because, we do the same, we perform the same argument for every edge. It is, for every sequence, for every finite set of edges, you have a limit by Kolmogorov extension, this thing. And of course, we will call this thing the wired, right? So I'll call it the wired uniform spanning forest. These are two measures that need not be the same, right? So of course, the first question that you can ask is, are they the same? And indeed, this is a more delicate question. And they are the same, for instance, on ZD. But let's just give an example that they need not be the same. Let's look at the example of an infinite tree. Right, an infinite regular tree. What will be the free uniform spanning forest on the infinite 3 regular tree? Sorry, it's a singleton, which is the whole tree, right? Because when I look at any big ball or big exhaustion of an infinite regular tree, it is a tree itself, right? There are no cycles, it's connected. So the UST has to equal it itself. So every edge will be in the UST with probability 1, right? So the free uniform spanning forest of the infinite regular tree, so example, the D-regular tree, right? The free uniform spanning forest equals, let's call it TD, equals TD with probability 1, right? It's a singleton and contains all the tree. However, so every edge appears with probability 1. However, in the wired case, the probability that an edge exists is not 1, right? Why is that? Because here is the edge that I'm trying to control. And here I have a regular tree going in one direction. Right, so let's say this is the 3 regular infinite tree. And here I have another, the tree goes in both directions. And I'm taking a big chunk, right? I'm taking a big exhaustion. So I'm cutting it at level n. And I'm asking, what is the resistance between x and y? So previously, if I just had the tree, then this is a finite tree. Right? The resistance is just 1, because there's just one path. But now I'm adding a new vertex. Right? I'm adding a new vertex here that is connected to all the edges here, right? And all the edges here. Etc., etc., etc. Right, so you see that what you have here is an instance of the parallel law. Right? Between x and y, I will have an edge with resistance 1. But there's also finite resistance from here through to this vertex, right? And this from this vertex to this vertex. Right? There's positive probability that I will be sucked into infinity and find myself back in y from the other side of the tree. Once I reached here, the probability of visiting x and y first is 1/2. Right? So you can see here that because of the parallel law, so here I have 1, and I have, I'm shrinking this, or I'm using electric theory to put another edge that has finite resistance. So the total resistance between x and y is less than 1. Hence, there is positive probability that this edge is not going to be in the wired uniform spanning forest. Right? So the wired uniform spanning forest is just a different measure. Right? Because I showed you that the probability of one edge being there is not the same. So in the wired uniform spanning forest, it is not this. Let me not write anymore. All right, is this convincing? In fact, you can convince yourself, this is perhaps a 2-cigarette exercise, that the measure, how does the measure look like? And it looks like drawing an infinite path, right, and hanging on it critical branching process with the correct distribution. So the wired uniform spanning forest, in this particular case, you can describe its distribution precisely. Okay, so these can be different, and there's a theory. So here there's actually a well-constructed theory. You could, given a graph, there is a theorem that tells you, is the wired and uniform spanning tree different or not? But let me not get into this theory, because I want to tell you something about planar graphs. Question? Okay. So this construction of Gn star and Gn has a very nice meaning when we're dealing with planar graphs. So let's, and it works very well. And what you get, essentially, let me tell you what is the bottom line of what I'm trying to show you, is that I'm considering now an infinite planar graph. And let's assume that it's great, that it's all the faces are finite, and it looks, and it's one-ended, and has bounded degrees. We don't need all these assumptions. If you want to read more about what are the precise assumptions that we need, you're welcome to consult the paper. But let's just imagine of a good planar graph. And we can draw the free uniform spanning forest on it, no problem. Right? And we can also draw the wired uniform spanning forest on it. They will not necessarily be the same. But I can also look at the dual graph of my planar graph. Right? The dual graph is the graph where I have each face is a vertex, and I draw an edge between two neighboring faces. Right? This is the dual graph. And the claim is, and every tree on the planar graph, right? Every tree on the original planar graph, I could take a dual of the tree. Simply, if I have an edge, right, in the original graph, it separates two faces. Right? If this edge is in the tree, then the corresponding orthogonal edge in the dual graph will not be there. And if the edge is not there, then I will put the edge in the dual graph. Let's make a picture that will make this completely clear. So let G be a finite planar graph or map. right? And I denote by G cross. This is the standard nomenclature. G cross, it's planar dual. Right, so if my graph is, let's just take the example that is easy to draw. This is my graph. The planar dual is going to be, I'm drawing it in, I'm putting a vertex in each face, including the outer face, and putting an edge whenever two faces are next to each other. Right, and I'm also adding an edge for the outside face. This is always the rule. So in this case, I will add this face. And now, just by the drawing, you see that there's going to be some nice connection to a star exhaustion. Right? That comes up naturally from the dual graph. Right? So we'll say that in a moment. And furthermore, not only can I define the dual graph given any spanning tree, so given T spanning tree of G, I can define T dual as in the picture, right? So let's say I take a tree, a spanning tree on the, let's draw another picture here. I take a spanning tree on the white edges. So if this was my graph, right? Let's take a spanning tree, which is, I'll take it the easiest. Okay, not the easiest. Here it is. It is not a spanning tree yet. Now it's a spanning tree. Bottom. Oh, yes, thank you. Okay, so now the orange edges are a spanning tree of my finite graph, right? So the orange edges are T, and I can obtain immediately, just by using the planar duality, I can obtain the graph, the spanning tree of the dual graph, T cross. My grandmother would not be happy that I'm using the cross symbol so easily, but that's fine. What is the spanning tree of the dual graph? I'm just putting an edge every time. I'm not putting an edge every time two faces are bordered by an orange edge, but I'm putting an edge every time I do not have an edge in the orange tree. So I'll put an edge like this, right? But on the outer face, I have only one vertex. So I'm putting an edge like this, right? I'm putting an edge here, 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 right? Here I'm going to the outside, so I have to connect it to this tree, to this vertex. Here I'm also going to the outside, so I have to connect it here. I didn't finish the drawing. Here I'm also connecting it. Here I'm also, and it seems right. Yes. So this is T cross, right? And you should agree with me that these are in complete bijection. If I start with T cross, I immediately get T, right? So this is that. So to get T, we're simply saying that E cross is in T cross if and only if E, the dual of E cross, is not in T. Okay, so this relation defines to you the bijection between the trees and any finite graph. So what do we get from this? So let me tell you the claim that now we get immediately just by this observation about the infinite case, right? So the claim. So now let G be, let's say, planar. Let's add one-ended, even though we don't really need it. Planar, one-ended. So in particular, it's infinite, right? The removal of any finite set leaves on the outside precisely one infinite component, and finite faces. So there are no infinite faces. right? So in particular, the dual graph is also a planar graph, and also has, the dual graph itself has finite degrees, it's locally finite, and all its faces itself are also finite, right? So just like in Z2. So in this particular case, we can employ this duality and get some connection between the limiting measures of the wired and free uniform spanning forest on G and its dual. What exactly is the connection? And here it is. If F, so I'm writing F is drawn from the free uniform spanning forest of the graph G, right? So I'm drawing this F by taking bigger and bigger boxes in my graph, not wiring, right? Leaving free boundary conditions, drawing the UST, and I get a certain limit. Then, if I take its dual, right? I can define here a dual for infinite trees or infinite forests as well. It works in the same way. Then F dual, which is defined combinatorially, given every F on given every spanning forest on G, it corresponds to a spanning forest on G tilde. You have to convince yourself, by the way, I didn't do it in this picture, that T forest, T cross is indeed a tree, right? It cannot have cycles because cycles would correspond to isolated vertices, or to if you have a cycle in T cross, then T orange will be disconnected, right? And if it will not be spanning, right? If you have a vertex that then it corresponds to a cycle in the orange, right? So it really works out nice. But the issue is that if I draw F from the free measure on uniform spanning forest on the big planar graph, its dual corresponds to the wired uniform spanning forest on the dual graph, right? This is distributed as the wired uniform spanning forest of G cross. Yes?
But it seems like if you take the dual of the forest, it's not always a forest because there can be cycle.
Yeah, so that's good. That's a good. You have to use the fact that all the components are infinite, right? So you cannot have a cycle, right? A cycle in the infinite case would correspond to a finite component. Did everybody understand Mikhail's? Did I'm saying it right? Question? Right. So Mikhail was worried if I look at a forest, right, and I have a finite tree, the dual forest will have a cycle. But in here, right, all the trees are infinite. So you cannot have a finite cycle in the dual graph. All right, and what is the reason for this? What is the reason? Sorry? It's just because of the wiring procedure. Imagine that we have this n by n box in Z2. The argument that I'm telling you now works for any graph like this, not just for Z2. And I'm making it larger and larger, right? When I look at the dual graph, right, and so I have Gn in my original graph, right? So, and Gn is an exhausting set of G, right? So let's even write the reason. Let's even write the reason here. Reason. I'll write it because it's exactly precise. But if Gn exhausts G. Sorry that I'm writing right here, then what will be Gn cross? Right, now I have finite planar graphs. Think about Gn as n by n cubes. Right, I look at Gn cross, it's going to be a cube with this new vertex outside. So Gn with this that is connected to all the boundary, right? Because this is the definition of, this is what we do in planar duality, right? So it will be a star exhaustion of the dual graph, right? So if Gn exhausts G, then Gn cross is a star exhaustion of the infinite dual. Right? So if you take a uniform spanning tree in Gn, you take its dual, so if T was uniform, you take its dual, now T cross is a uniform spanning tree of Gn cross, right? And this converges. This is just the definition, right? This is just the definition of the limit in the wired. When you wire, the definition of the wired uniform spanning forest of G cross. Who is unconvinced? Matthias, you're not convinced. I saw you move one bra, which is a... Okay. Anyone has a question about this? Don't be shy. Right? So notice that, just in case it's clear, and each finite exhaustion, and each Gn, when you take the cross, you add a new vertex, right? But this vertex does not exist in the infinite graph, right? So you can think about this new vertex that you add due to planarity as your infinite vertex. All right, so in the planar case, so now here's the theorem that I'm going to show you. So we want to discuss, right? I didn't just show you because of its interest, because I want to study this model, right? The natural free uniform spanning forest model. And I want to say, in this setting, G is planar, one-ended, finite. The theorem that I'm about to tell you is that this thing is almost surely connected. Right? And in fact, there's a higher level of generality that this holds. So, and this, as you will see, this is a harder model to study, but this, I will convince you soon that this is somewhat easier to study. But now we have a combinatorial condition. If this infinite tree is, what is a condition in terms of f cross that f is connected? Right? I have now an infinite uniform spanning tree, right, of some planar graph. Think about Z2, and I take the dual. What is the property of the dual that I will see? The dual tree.
No cycle.
Yes, but it already has no cycle. You're right, but it's no bi-infinite paths, right? A bi-infinite path is what you say is a cycle, right? Because it connects at infinity, right? So let's write this down and observe. If the dual tree, right, has a bi-infinite path, right? It's drawn in the plane. Everything is in the plane. So there's this famous theorem that we know that if you have a bi-infinite path, it splits the plane into two pieces. Right? So in particular, the original tree f will be disconnected. And this goes the other way around. If there's no way, if it is disconnected, if I have an infinite tree, then its boundary must contain, right, a bi-infinite path, right? And this bi-infinite path will be in f cross. Right? So let's observe. So this is the main observation. So and this is completely combinatorial, right? There's no probability at this point yet. So the observation is the following: f is connected, and again, I'm assuming here that right, it could have a cycle, but f, I'm thinking about it. This is a deterministic statement when I'm looking at a forest in which all of its components are infinite. Of course, if there's a finite component, then you will have a cycle. Right? But if all the components are infinite, f is connected if and only if f cross has no bi-infinite paths. It doesn't have bi-infinite simple paths. Right? There's no path that is isomorphic to z. No bi-infinite path. Or in other words, how do we call such a thing? So no component contains a bi-infinite path, or in other words, sorry? Each component is one-ended, right? Each component, if you have a tree, right, then Z2 is one-ended, but it clearly has bi-infinite paths, right? But a tree is one-ended means that it cannot have a bi-infinite path, and it's exactly the same thing, right? Because if you take any finite set, there's only one path going to infinity, right? So it's the same thing. But let's just say no bi-infinite path, but it means it's equivalent to saying that f hat, each component of f cross is one-ended. Okay. Any questions so far? All right, so this is a pretty neat stuff, classic stuff. Let me tell you what is the theorem that I'm going to prove to you. And this is, our goal is to study this measure, right? And the question is, again, as usual, is it connected? So this is a theorem together with my ex-PhD student Tom Hutchcroft. Uh, 15, 16, 17. When was it? Let's just leave the year empty. So under these settings, so let's say exactly what these settings, just for our proof. G is planar, one-ended, finite faces. Finite faces is like saying that the dual is locally finite. Finite faces. Let's even add bounded degree, even though it's not really necessary here. Bounded degree. Then under these, so notice that, for example, this includes both the recurrent or the transient case. Right? So the result of this theorem has nothing to do with the dimension of the graph or isoperimetric. It just is in some sense, a topological theorem. It just has to do with the planarity of the graph. Then free uniform spanning forest is almost surely connected. Right? So this is the theorem. And of course, by this observation, this is the same as saying that the wired uniform spanning forest, right, almost surely every component, there are only infinite components, has no bi-infinite path. So let's just write is one-ended. Right? There's only one way to escape to infinity. In particular, every component has to be a recurrent graph, right? A tree that has just one, right? Just one thing going to infinity has to be recurrent because everything on it is a finite bush, so the random walk can be projected on this infinite path. Okay. And the proof I chose to show you this proof because it is another use of everything that we have learned regarding circle packing and effective resistance. And here it is. So so as I said, the proof works both in the transient case and both in the recurrent case. So let me just show you the transient case. Unless you prefer to see the recurrent case, they're almost the same. So I prefer the transient case just because then you could draw the pictures in finite board space. So we assume our graph is transient. So the proof in the transient case. Right? And of course, I will want to apply the circle packing theorem at a particular spot. Right? So firstly, what do I need to prove? So here's what I need. So I'm only going to prove things about the wired uniform spanning forest. The free is too difficult for me to approach just by itself. So let edge be an E. Let E be an edge, x, y, an edge, right? And let AE be the event, right? That x, y are in two distinct components of F. The wired uniform spanning forest of F minus E. Right, this is just the event, right, that I have x, y, right, and that I have an infinite path going from x and an infinite path going from y. And I want to show that each component is one-ended with probability 1, so I have to show, so what I want to prove, WTP, is that the probability of AE and E is in the uniform spanning forest, the wired, right, that this is 0. Everybody agrees with me? Because then we learned that for every edge, the probability that this edge is a part of a bi-infinite path is 0. We have countably many edges. So for each edge, so the probability that it holds for some edge is 0. Okay, so this is what I need to show. Let me prove it to you. So now we're going to apply the circle packing theorem. Because what else can we do when we have a planar graph? This is the heart of the proof is right now. So we pack this, we know by the Hesheram theorem that we can, such a graph we can pack inside the unit disk. So circle pack in the unit disk in z smaller than 1, such that x and y are circles near the center. It actually doesn't really matter where x and y are. So here's the unit disk. Right? I'm plotting, now I'm drawing, I'm circle packing the whole thing. So the carrier is the unit disk. So here will be the circle of x. Here will be the circle of y. Right? And the rest of the graph is circle packed in here. And I imagine that there is a giant infinite circle packing so that the unit circle is the set of all of its accumulation points. And now I am taking an approximation of the event AE, right? So let epsilon be small, right? Some small number, and let B E epsilon be the event that, and now I'm looking, so I fixed an epsilon, and I'm looking at all of the vertices that are epsilon away, that they're circle packing, the centers of their circle is epsilon away from the boundary. So it's a distance at least epsilon from the boundary. So this distance is epsilon, and V epsilon will be everything that is inside here. Right? And the boundary of V epsilon is going to be all the points outside, right? That neighbors V epsilon. And I'm looking at the event B epsilon is going to be that the component, every component of F cross minus E intersects V minus V epsilon. So what this means is that right, this event is exactly the event that when I draw the uniform spanning forest, there is a path from x, right? E is the edge xy. So this means that there will be some part of the tree from x, right? That reaches, perhaps this is it, that reaches the outside, that reaches epsilon away from the boundary, perhaps in more than one point, and also the same picture from y. Right? So this is what I want to say. So you see that this, so what I need to show to you, so it's clearly that as epsilon becomes smaller and smaller, the intersection of all these events is exactly AE. Right? The intersection of the intersection over all epsilon of the events of these pictures gives you that x and y are in two infinite components, right? So let's write this down. AE is the intersection of B epsilon E over all epsilons, right? So what I need to show to you is the probability that E is in F hat and B epsilon E. I need to show you that this goes to 0 as epsilon tends to 0. Right? Which is a thing to say that if I condition on this pink picture that both x and y reach far, then the probability that x and y is in the wired uniform spanning forest goes to 0, right? Or is very close to 0. Yes?
You work on the dual with F cross?
So no, you're right. So I'm working F is F cross is the wired uniform spanning forest of the graph, right? The dual. So this is a good point. So let's just say I'm working with F, right? Not the dual, and F is just the wired uniform spanning forest. So F is the wired uniform spanning forest. Right, and the reason is because I can first take the dual of G, but the dual satisfies the same things. Right? The dual has the same properties. It's one-ended, bounded degree, or whatever. Right? So I just want to show that the wired uniform spanning forest on a transient planar graph like this is one-ended. Right? So we are here at this point, and now I'm ready to conclude the proof with a bit of hand waves. So what do we do? Let's draw the picture again. Here is the picture, right? And here are the two vertices x and y, drawn as circles, x and y. And I'm conditioning on this event, on b epsilon. I want to prove that the intersection of event is small. I will condition on this event. Right, and show that conditioned on this event, what I get, the probability that conditional on this event, that E is in F, is small. So I know if I condition on this event B epsilon E, I know that there's a path in the tree that starts from X and ends at the blue line. Let's draw the blue line again. Here it is. And now I want to find this path. Right, so what do? I start here. Here there is an edge that I don't know what is the status of this edge. I haven't checked if it's in the tree. And I want to find a path starting in X that belongs to the tree, belongs to F, that is the rightmost. Right? I want the rightmost with respect to this blue edge. So I want this path to go as much as I can to here. How do I do that? I'm just starting to explore and asking every edge, are you in the UST or not? But I'm doing it in a clockwise or counterclockwise order. So I'll first check the edge that is the rightmost edge, right, bordering X. Perhaps it's in the USF. I'm drawing it, right? And then I check the edge right next to it, right, that points the most right, right? And that one is not in the USF. So I just leave it. And now I check the next edge in the ordering that will be the most right. And this edge isn't here. It is in the USF. That's great. So now I have perhaps a few other closed edges. And perhaps that's it. I have no more other open edges. I go back to the vertex that I was here. And I check the next edge. Right? And I continue this way. Right? Until I discover this path. And I've discovered perhaps all sorts of parts of the tree here, right? And a bunch of closed edges, a bunch of edges that are not in the UST. Right? And now I do the same thing from Y, except that I'm discovering a path that goes to distance epsilon from the boundary that is the leftmost. Right? So here I'll try to make the path that goes as much as I can to the left. Right? So perhaps it starts with here. But now these are closed edges here, here, here. Something like this. And here I've discovered some other parts of the tree, but it only goes into this section inside between these two long paths. Right? So the status of the edges that I see between these two paths is very unclear to me. Right? I don't know what I discovered there. But everything that is in here is wide open. I haven't checked the status of the edges there. So they are not conditioned on anything. And now I use the Markov property, and I say, now I have to draw the graph on the UST on this graph when I conditioned on the entire configuration that I discovered here. So I conditioned on some of these edges being open, some of them being closed, but it looks like this. And when I condition all of these pink edges are joined to be one single vertex. So I have one vertex here and one vertex here. And the probability that this edge, xy, is in the tree conditioning on all this is going to be the effective resistance between here, between this vertex, the the pink path on the left and the pink path on the right. And now I want to convince you, using our circle packing machinery, that this resistance is small in terms of epsilon. Why is this true? Let's look at this drawing. And I want to convince you that the resistance between this vertex to this vertex is small. Right? And this is a big vertex, right? It's a whole path. But because I'm in the wired uniform spanning forest, I can always imagine that I have a vertex in infinity that is connected to everything. So what I will show you, in fact, that the resistance between this vertex and infinity is small, and also the resistance between this vertex and infinity is also small. And then because and then it implies by the triangle inequality for resistances that the resistance between the two things is small. So does anyone see the reason why the resistance of the leftmost, say, in this drawing, the leftmost pink path is small? Sorry? Something like? Random flow. Yes, that is correct. But what is the random flow? So what did we learn in our basic moral of circle packing, which is good to close the talks with? If we have any shape, any reasonable shape, right? And here we have, and here we have put, and here we mark this side of it in blue and this side with blue. And inside we have a teeny weeny circle packing of everything, right? Then the effective resistance between this side and that side is bounded above and below by a constant, right? If it's we use this fact if it was a square. We use this fact, for instance, when we have a circle here and a unit circle in the middle, and here the resistance here is a constant. We used it to prove recurrence, but we know that it is a constant. In particular, it's bounded above by a constant. So here, the distance from here is epsilon. So I could put here log of 1 over epsilon annuli that connect this pink path from the left to infinity. Here's one, here's the second, here's the third, here's the fourth. Right? And in each one, the resistance from the pink to infinity is a constant, and I have log many of them. So by the parallel law, the resistance is at most a constant over the number of annuli, which is log. Right? I do it the same here, and I get that this probability is bounded above by some constant divided by log of 1 over epsilon. This is nice. But there's only one caveat. What happens if the drawing doesn't look like this? What happens if the drawing, as much as I tried to make them close, I didn't succeed, and in fact, they look something like this. What if this is, the leftmost path, it turned out to be something like this, and everything here I cannot touch, and now the rightmost path turned out to be something like this, right? And so they are very close to each other, right? And I can't do this. So now you argue that in fact you could put here many annuli, as long as they are close to each other from here. Or, sorry, I should have done it this way. Right? So you just observe the two typical geometries that you can get. Either they are close to each other from this side, and then the resistance to infinity is small, or they're close to each other, and then the resistance just to themselves is small, and this gives you the proof. In the paper with Tom, you can see the full details, better drawings, more generalities of these things. And if you're interested in uniform spanning trees, there are many references there. I hope you enjoyed this course. You're welcome to email me with anything that you want. And I hope to see you soon in our research endeavors. Thank you.